CS229, lecture 18. The topic for today, we'll be continuing our study of unsupervised learning. So the topics today is, we're going to wrap up factor analysis. We mostly finished up factor analysis last time, except we just stopped at the end where we finished the derivation and didn't really have time to kind of answer some of the pending questions and really get a good feel for factor analysis. It almost felt like, you know, monstrous looking expressions and that's it. But let's kind of quickly revisit factor analysis to get some better understanding of what's happening under the covers. It's a lot easier than it looks. And then the plan is to finish up principal components analysis and maybe start ICA, independent components analysis. I'm not sure how much time we'll have for this, but hopefully we'll at least start this and if possible finish it. Right, so a quick recap of the last lecture. The last lecture, one big proof that we covered was the convergence of the expectation maximization algorithm, and the proof was pretty simple. It was we wanted to show that the EM algorithm is guaranteed to increase the likelihood of our of the observed data in every step, in every iteration, right? And the way we went about doing that is to show that the likelihood at theta of t plus 1, we want to show that it is greater than the likelihood at the previous theta of t. And the way we went about doing that is to show that the likelihood is greater than the elbow. You know, Jensen's inequality tells us that the elbow for the same at the same parameter value, the elbow for any value of t, any value of q will always be lesser than equal to. That's Jensen's inequality. And then we saw what happened when we switch from theta t plus 1 to theta t, and this basically was the m step at time step t. So that at the m step of time step t, we optimized theta to obtain theta t plus 1 such that the elbow was maximized. So theta t plus 1 is the maximizer of this of the elbow at qt. So therefore, at theta t, the elbow value will always be lower. And then we saw from the corollary of Jensen's inequality that that the elbow at theta t and qt is equal to the likelihood at theta t, right? So it was 3 simple steps, and we also kind of saw the pictorial intuition for this. So at theta t, let's call this, this pen is not good. Yeah. So this is elbow of qt theta t, right? If this is theta t, where it is tight at the likelihood. So this is just L theta, and this is the elbow where at theta t it is tight, and then we maximize it, and we get theta t plus 1, and we construct a new elbow that is tight at theta L t plus 1. So this elbow is this, and this elbow is this, right? And so we got that L of theta t plus 1 was less than the likelihood at theta t is less than likelihood of theta t plus 1, right? So that was the EM proof. And then we moved on to factor analysis, where in factor analysis we were interested in the case where we want to model x's that live in a d-dimensional space, but we have n number of x's where n is much smaller than d, right? And in these cases we saw that modeling it as a simple Gaussian will give us singular covariance matrices, and therefore we instead what we want to do is to have a latent variable corresponding to z that lives in a low dimensional space, and have a matrix L from which the low dimensional space is mapped up to a high dimensional, a d-dimensional space, and there is some extra noise added in the d-dimensional space, right? And so the model was defined like this: z comes from a low dimensional Gaussian which has just k dimensions. So in this problem, k is less than d, but k is greater than n, right? So this is the assumption we are operating, where n is much smaller than d, but k is also smaller than d, but k is bigger than n. That's the setting we are working in. Hold on, did I flip it? So we want k should be less than d, but d is much bigger than n, but we want n to be greater than k. Yeah, that's better, right? So we want so Z lives in a k-dimensional subspace, and it's normally distributed with mean 0 and identity covariance. And then X given Z, we assume is generated in this way, where mu, L, and psi are parameters, right? So mu is like an offset for in the x-dimensional space. So once we map Z to high-dimensional space, it will still be in mean 0, right? So this is like an offset that we add, and psi is some kind of an extra covariance, an extra diagonal matrix, where each dimension in the d-dimensional space has an independent noise that's added, right? So at first these might seem pretty arbitrary choices. However, if we kind of visualize what's happening, basically what we have is this process can be visualized like this, right? So from this we see that x minus mu is distributed according to mean LZ and some noise psi. So we can think of the set of z's, the set of latent variables that we have. Imagine we have, you know, a design matrix of these z's, right? Just like in linear regression. So each zi is one example. We have n such examples which are of k dimension. And then suppose we have, you know, L1, right? Consider L1 to be like theta, right? So we have this theta, which is like, you know, a parameter, and when we multiply this design matrix by theta, we get one set of one column over here, right? So you can think of this as d independent linear regression problems, right? So L is d by k, and k and the k matches the dimension of the design matrix. So think of this as the design matrix, and think of this as d theta vectors, and think of this as d label vectors. Right? So what's happening is, for each dimension in which x lives, we associate a parameter vector. That's one way to think of it. We associate a parameter vector, and we get a noisy observation, which is x minus one column of x minus mu, right? And we have so this in linear regression we had a design matrix, one parameter vector, which we tried to fit to one column vector of y's. So this was y, this was theta, and this was x. But here, you know, the terminology is different. We have a z design matrix and d different parameter vectors, you know, d different, and for each vector we have, you know, a different label, right? So you can think of this as d different linear regressions happening simultaneously. Any questions? Any questions here? Right? Yes, question?
So it's like the betas we saw that it's going to represent every single dimension separately for the
Yeah, so every single, exactly. So every single dimension in the d-dimensional space, you can think of the column corresponding to every single dimension in the larger space, you know, is like a label vector for that linear regression. We're going to come to projections soon. Yeah. So for now, you know, this is the setting we are operating, and we subtract x minus mu. You can think of mu as being the bias term, right? So bias term, you can add you know, each component of mu. You can think of it as a bias term you're adding to each of the d problems, And so if you subtract the mean from x's, you get this kind of a setting where this is like a linear regression problem. And in linear regression problem, we also assumed that y was equal to theta transpose x plus epsilon, where epsilon was independent noise, whereas over here we are doing x minus mu is equal to z L plus psi I. So this is one, you can think of this as zi, and this is the first row. So this is like zi transpose L1 plus psi I, where this is the diagonal matrix that we are adding, right? So this model is basically trying to represent d different linear regression models in vectorized notation, where all of them are written in this kind of a matrix notation, whereas previously we had this matrix vector notation, right? That's all that's happening here. And from this we constructed the E step and the M step, right? So the E step was pretty straightforward. So Qi was this, so Qi we set it to be the posterior distribution at the current values of mu, L and psi, and this notation is pretty straightforward. It is just the conditional of the Gaussian. We've seen this kind of notation in Gaussian processes as well. So for every I, for every example, we set Qi to be a normal distribution that has this mean and this covariance. And these are just, if you remember, this comes from the Schur complement, and this follows the notation where you consider so much to be like the z value of the x variable, where you subtract the mean divided by the variance, and then you this also has like the correlation coefficient embedded in this, and then you multiply it by L transpose, right? So this is just like transforming in the case of multivariate Gaussians, and this is the Schur complement from which we get the covariance of z given I. So the goal here was we calculated zi given xi, and that's Qi, right? And from this we come up with the M step. So in the E step we always estimate the latent variables, and in the M step we re-estimate the parameters, right? That's going to be common for any model, including Gaussian mixture model and factor analysis. So in the E step we estimated the latent variables zi, and in the M step we re-estimate the parameters, where L, mu and psi are the parameters. So L, we had this monstrous looking expression. Mu was just the mean of the xi's. That should be intuitive, right? Because we are just what we are doing is transforming z via the L and adding some mu. So Lz has mean 0. So obviously the maximum likelihood estimate of mu will just be the mean of x's. And in fact, that will not change from iteration to iteration, right? So that's just going to be mu. So you calculate it once, and in the next M step you can just reuse it. There's nothing that changes here. And this psi I was this even horrible looking expression, worse than the L expression for the L, and that's where we stopped last lecture. However, even though these look pretty scary, we can actually kind of dissect this a little more and get a better understanding of what's happening, right? So first of all, let's start with the L. Right? So to make this understanding easier, I will introduce some new notation, right? So mu of mu zi given xi, right? So mu of zi given xi is the mean of the posterior distribution that we obtain in the E step, right? It's a Gaussian that is concentrated at mu. So you can think of this as, loosely speaking, let's call this kind of z hat I, right? So it's our best guess of what z is, given our knowledge about x's. Right? So this is our best estimate of zi. Right? Does that make sense? It's just our best guess or best estimate about zi given what we know about x. So that's one notation. And now xi minus mu, or let's and we also have this term L mu zi given xi. Okay. So now L times mu of zi given xi is equal to basically L times z hat I. Right? We just defined, we saw that mu of zi given xi, we can think of this as our best estimate of z. And L times zi, we see that L times zi is our best estimate of x minus mu. Right? So L times zi, think of this as our best estimate of xi minus mu, and therefore we will call this x hat I minus mu. Right? So L of mu zi given xi is just L of z hat I, and that's the same as x hat I minus mu. Right? Now once so what can we think of this as? So think of L z hat I to be the reconstruction of x. Right? So z hat I is our best guess of what z is given x is, and then L times z hat xi is what is now we are going from z back to x. So you can think of L z hat I plus mu to be the reconstruction of x. Right? So over here, plug in z hat xi here, multiply it by L, and we get x hat minus mu. Right? So this is like the reconstruction of xi. So that expression can now be written as L is equal to sum over I equals 1 to n xi minus mu. So xi minus mu, let's think of it as yi, following the linear regression example, and mu of zi so mu of zi, let's call this. So mu of zi is basically this entire vector z. So mu of zi is our estimate of the z vector. So let's just, so I'm just going to call it capital Zi transpose. Okay. And here again, this basically is you can think of it as z transpose z plus some covariance inverse, or if we take the transpose, we get we don't need the transpose. So this is basically like you can think of this as L transpose is equal to, this comes here, z transpose z plus something inverse z transpose y. Right? So basically we are doing some kind of a regularized linear regression. Right? That's what's happening in the L expression over there. Right? So we make our best guesses about z. We have x's that are given to us, and using those best guesses for z, we update our L, and for that we are just solving d different linear regressions in parallel. right? So that's L. Now, what about psi? Right? So psi is also this, scary looking expression, and we're going to use, the same terminologies in there as well. So what we end up getting there is something like, you can think of this as, I equals 1 to n xi transpose, and now in place of mu of zi, so over here, let's call L mu to be x hat. So that is minus xi, x hat I transpose, and then L mu is again x hat I minus x hat I xi transpose, minus, if we expand the matrix on the other side, we get plus L mu, think of it as x hat I x hat I, and the L comes from the other side, x hat I transpose, plus L sigma zi given xi L transpose, right? And now this can be written as I equals 1 to n xi minus x hat I xi minus x hat I transpose plus L times zi given xi L transpose, right? So this, if you recognize, what we are doing is we are taking the correct label minus our estimate of the correct label, right? And this is therefore similar to estimating the noise in linear regression, right? So in linear regression, if y equals theta transpose x plus epsilon, the way to estimate epsilon from your data is to first find out theta hat and then do 1 over n I equals 1 to n yi minus theta hat transpose xi I square, right? So this is the way we estimate epsilon in linear regression if we need to. And similarly, we are estimating this psi, which is the noise that's getting added to xis, right? And this, because of the notation, turns out to be a full matrix. However, we are interested in each of the d examples independently, and therefore this matrix that we obtain, we are just going to take the ith element to be ith element of this. This is basically like saying we don't care about the covariance of the noise between one linear regression problem and another linear regression problem, right? So we are just ignoring the off diagonal elements here. Right? Does it make sense? Any questions?
How did you get the L matrix?
So the L matrix is what we have in the update. That's, or was it a different question?
Also, what I'm not sure what x hat in this case.
So x hat, you can think of x hat as, so if we so you can think of factor analysis as this. You're given the y labels for different problems, right? And by just having the y labels, you want to construct both the covariates as well as the parameters, right? It's a really hard problem, right? You're given x's and you want to estimate both z's and l's. L's are the parameters that's part of the model, right? And zi's are the latent variables that's specific to each example, right? So our goal is to not only estimate what our design matrix was, but also estimate what the parameters was by just having the labels, right? Which sounds kind of impossible, but given these modeling assumptions that z's come from a normal distribution, and that they follow this kind of a linear relation, you can apply EM algorithm to this and you can estimate it. There was another question? So you can think of factor analysis as this problem where you're given just the labels for d different problems, right? And you're assuming a linear modeling of some hidden covariates. We don't know the design matrix. We don't know the parameters. And we are estimating both the design matrix and the set of parameters given just the labels. Right? It's kind of magical. You're just given labels and you're estimating both what your x's were as well as the parameters, with only the assumption that the inputs are distributed according to some kind of a normal distribution with mean. Right? And mu here just ends up being the bias term, one per linear regression problem. Right? Yeah, so this looks kind of monstrous, but if you think of each of these L mu to be like x hat, right? Then you can visualize this as estimating just the reconstruction noise between x and x hat, and we are only interested in the diagonal elements here. All right, so that wraps up our coverage of factor analysis. Oh, and I think there was also one question which a student asked: by doing all of this, how did we actually go about solving the singularity problem? Where so if you remember, we briefly wrote this notation that for factor analysis, log p of x, or the marginal likelihood, actually had this closed form expression where it turns out to be, or x happens to be a normal with mean mu and covariance L transpose plus psi. Right? So the covariance matrix estimated for the marginal of x is therefore this LL transpose, which is a low rank matrix, plus a diagonal matrix. And because we are adding a diagonal matrix to this low rank matrix, we are guaranteed that this is no longer singular. Right? All right, so let's move on. So this basically wraps up factor analysis, and now we will start principal components analysis. PCA. PCA. So in factor analysis, our goal was to model x's as something that approximately lies in a low dimensional space, right? So for every x we had a corresponding z, and z lived in a lower dimensional space, and the relation between x and z was what you call as affine. Affine is another word for linear plus some offset, right? So L gives us from z to the centered x, and then you add some kind of an offset. So x and z are related by what's also called an affine relationship, right? So and we had to go through this EM algorithm because we were modeling it with the assumption that d was much larger than n, right? PCA is another approach to where you're given xi's, I equals 1 to n, and xi is in D. And now here we no longer assume that D is much larger than N. We are back into the usual regime where we have, generally have a much more number of data points than the dimensions of the space. And now we want to find out if our data actually lives in a low dimensional space, right? So for example, if here's one example. So if this is a data set where we are plotting, so this is x1 and x2. So if you have a data set where you are plotting, the example in the notes is supposing you are you fly helicopters, or you fly toy helicopters, whatever, and for every such pilot, you have a skill level and the level they enjoy flying the helicopter, right? And if you're trying to if you look at the scatter plot of skill versus enjoyment, you wouldn't be surprised if you see some kind of a linear relationship between them. And it's more or less because people who enjoy flying helicopters are likely to be good at it, and vice versa, right? So even though you have two different variables, they are kind of reading off this underlying common common trait of the pilot. You can call it piloting karma or whatever, and and therefore these two are pretty correlated. And now your data may therefore have, if your x's in general, so if you have n examples and d features, right? So some of your features may be kind of correlated. So if you have if this is a data set about pilots, and one of the features is their skill level, and another feature is the level of enjoyment they report flying helicopters, right? Even though this looks as a d-dimensional space, because some or many of your features may kind of actually live in a lower dimensional space, your entire d-dimensional space can probably be represented in a lower dimensional space, which is k. Right? By this, I don't mean element-wise similar. We are just thinking of representing this high dimensional data in a low dimensional space. Yes, question?
How is this not a supervised setting? Because you can select one of those to be acting as y and then try to find the best parameters.
Yeah. So the question is, why isn't this supervised learning, where you can think of one of them, you can take one of them to be y and kind of regress it from the others. You can do it as a supervised learning problem, but the problem is in general quite hard, in the sense you don't know upfront which label, which of these features you want to choose as your y label. You can try it with all of them. You can try a subset of them. It's not clear how to go about actually solving this as a supervised learning problem. What if d is 10,000, right? Are you going to perform 10,000 linear regressions? You could do that, but PCA is much more efficient.
But if one of them is linear based on the others, then whether you choose any of them, they will have a linear relationship, right? Choose any of those.
You could do something like that, though this is PCA, as you will see, is much more straightforward. You don't have to pose it as a supervised learning and learn it, etc. So it's PCA is more straightforward, right? So in PCA, our goal is to therefore find subspaces of our data, find a subspace in our input space where the data kind of lives. Right? So in PCA, the first thing we do is to center our data and scale it to have variance 1. What we mean is, the first step in PCA is to standardize your data set. Right? which means we want to set x j I to be x j I minus mu j divided by sigma j, where mu j is the mean of the jth column and sigma j is the standard deviation of the jth column. Right? So first thing is independently kind of center each column and scale each column so that the column has variance 1. Okay? So that's the first thing, where mu j is 1 over n I equals 1 through n xji, and sigma j square is 1 over n I equals 1 to n xji minus mu j square. Right? So the first thing is we want to standardize our data set to have mean 0 and standard deviation 1. And the reason we want to do this is it may so happen that the units in which your data is represented can be very different. So for example, if you're representing, for example, the height and weight of a person in a data set where each row corresponds to a person, height may be, you never know, the weight may be represented in kilograms, but height may be represented in millimeters. Right, so the values in the height column will generally be much bigger than values in the weight column, for example. Right, so the first thing you want to do is to kind of become agnostic to the units in which your data is represented, and for that we just standardize each of the column independently. Right? And once we do that, the way we want to find the underlying subspace is like this. So, right, so let's assume this is x1, xd, and if your data is right, so we could try to find a subspace here and project all our points onto the subspace. So this is one possible projection. So each of the crosses were the x's that lived in the high dimensional space. Right? Right? So this is one way to this is one possible low dimensional subspace onto which we are projecting all the individual data elements onto the low dimensional subspace, right? And another possible subspace is x1, xd, and trying to draw the same things here. Now, what if instead we chose this to be our subspace, right? If well, there is one technical error in what I did. The subspace must span through the origin. So instead, let me just redraw the axes so that let's assume this is xd, right? And it's going through the origin. So instead, we could also have this to be the subspace, and if we can project all the points onto our subspace. Right? If you remember, projection means to find the closest point on the subspace to the point which you're trying to project. Right? So, and the natural consequence of that is that the line connecting the projection to the point will always be perpendicular to the subspace itself. Right? So we could have, there are an infinite number of subspaces that we can come up with, right? And we could either use, this is one possible subspace onto which we are projecting. This is another possible subspace onto which we are projecting. But PCA tells us that the subspace onto which you want to project your data should be the one where the variance of the projected points is maximized. What do we mean by that? It means, so if you look at the projected points in this example, they're kind of clustered within the space. And if you calculate the sample covariance, it would be it's of some value. Right? However, with this we see that the projected points are much more spread out. Right? This is much bigger than this. Right? It's the same points but different choice of subspace. But the variance of the projected points, the projected points in this case are much more spread out compared to the projected points here. And PCA tells us, or what PCA does is to find this low dimensional subspace, this k dimensional subspace of this d dimensional space where the projected points have maximum variance. Right? So it's a variance maximizing procedure where we find a subspace such that the projected points on the subspace have highest variance. Right? And the way we represent the subspace is through these unit length vectors. So the idea behind doing something like this is that we want to retain as much of variance there is in the data to the extent possible, even after projecting it down to a low dimensional space. We don't want to lose the variance. We just want to lose the number of dimensions where the data lives. We want to project onto a lower dimensional space, but we don't want to lose the variance in our data. We want to retain the variance in the data, but lose just the dimensions. That's the idea with PCA. Right? So suppose suppose we represent the low dimensional subspace with unit vectors u. So if u, you can think of u in Rd to be unit length. Right? So if u represents a basis of the subspace of unit length onto which we want to project our data. You might remember from one of our earlier lectures, if u is a basis vector, the projection of x onto the space spanned by u will be the projection matrix of u times x, where x is the point that you want to maximize. And so that would be the projected point, and this the projection matrix of u is basically u transpose over u transpose u of x. Right? That's just the projection matrix of projection matrix. And we see that u transpose u is just 1, and so the projected point will be just xi transpose u. Right? So this will be xi transpose u. This is a scalar times u. Now what we want to do is to find u such that the variance of across these projected points is maximum. Right? So if we have n examples, what we want to maximize is for all n examples the norm of this projected point. So the norm of the projected point is basically the length from here to the projected point. Right? if we find u such that the sum of the squares of all the projected lengths is maximum, then effectively we would have performed PCA. Okay? So what we want to do is find u such that 1 over n sum I equals 1 to n, the norm of the projection of u times x square is maximized, right? And this is the same as 1 over n I equals 1 to n x xi transpose u. So this is just a scalar times u. Norm is maximized. So we want to maximize this, or rather u is equal to argmax of this, right? And this we see that it is some scalar times a unit length vector. So the norm of this whole thing is just 1 over n I equals 1 to n xi transpose u square. Right? So the norm of a scalar times a unit length vector, so the norm of that is just the square of the scalar itself. Right? And this we can now write this as, so I'm going to continue here, right? And that is equal to u transpose 1 over n I equals 1 to n xi transpose u, right? And because our x's were centered, this thing has mean 0, and therefore this entity over here is the sample covariance matrix. Right? So you might remember this from some optimization class you took. This u equals argmax u of u transpose some matrix u. In this case, this happens to be 1 over n I equals 1 to n x I transpose. Right? Does anybody know what the solution of u is for this problem, where u is a vector? So u in this case is identifying, so if you solve this, the solution u is basically the eigenvector corresponding to the largest eigenvalue of this matrix, right? And that's because, right, argmax of u transpose au will give you eigenvector of largest eigenvalue of A. Right? And this analysis holds where instead of u, if you have, where here we just considered one u, one vector, but if you consider a whole basis of basis vectors, then nothing in this argument changes. By performing this maximization, you would have recovered where instead of a single u, if you had k u vectors, then by performing this maximization where instead of one vector you have k u vectors, you will have recovered the top k eigenvectors corresponding to the largest eigenvalues. Yes, question? So how we went from here to here? Yeah. So So this step, I'm going to write it here, 1 over n I equals 1 to n xi transpose u square, right? And this is the same as 1 over n. So I'm equals 1 to n xi transpose u xi transpose u. It's just the square. And this we can write it as 1 over n I equals 1 to n xi transpose u. And this dot product we just write it the other way, and then we get u transpose xi. Rather, I should have done it the other way. So instead, if we had swapped this, we'll get I equals 1 to n u transpose xi transpose u, right? And then you can take the u common out of all the summation, and that gives us u transpose 1 over n I equals 1 to n xi transpose u. Right? So basically, by following this variance maximizing argument, where we want to maximize the sample variance, or the projected points onto our subspace must be as far as possible from the origin, right? By following this variance maximizing principle, if we find the bases u such that the projected variance is maximized, we will see that we will end up with an eigenvalue problem where we want to calculate the eigenvectors of the sample covariance matrix of x's, right? So if x is our data matrix, PCA tells us that first calculate x transpose x, right? X transpose x is basically this, written in matrix notation. Take x transpose x and calculate the eigenvectors and eigenvalues, or calculate the spectrum of the x transpose x, and depending on the number of subspaces that we want to retain, so x transpose x will give us a collection of lambda I ui, so say lambda 1 u1, lambda 2 u2 until lambda d ud, right? These are the d eigenvectors, eigenvalues, and u's are the d and u's are the d eigenvectors. And now what we want to do is if depending on the amount of variance that we want to retain, a common practice is to then choose as many lambdas or as many pairs of eigenvectors such that or a more precise way to say it is find k such that sum over I equals 1 through k lambda k over sum over I equals 1 to d, lambda I. This is equal to some kind of a percentage, say 95% or something, right? And it's common to choose k in PCA by first performing the eigen decomposition of x transpose x, right? And then by sort your eigenvalues in some kind of a decreasing order, and then find k such that the sum of the first top k eigenvalues divided by the sum of all the eigenvalues is some a percentage of your choice. And by choosing k to be 95%, you can effectively say that you've retained 95% of the variance in your data, even though you went down from d dimensions down to k dimensions. This question?
So the last thing that you said there, I've seen some implementations that do exactly that, but they use singular value decomposition.
Yeah. Yeah, I'm going to come to that right after this. Right? So, any questions in this? The way we go about doing it is to take X transpose X, take the eigen decomposition of X transpose X, obtain the eigenvectors of X transpose X, and then choose K such that the sum of the top K eigenvalues divided by the sum of all the eigenvalues is the fraction of variance that you want to retain. So if you were to plot, let's say this is K and this is fraction of variance, you will generally see that if this is D, then you will generally see that this goes down something like this, where or rather this is D minus K, which means if you were to prune out all the D eigenvectors, then you will be having 0 variance remaining. But if you prune 0, you'll be having all the variance remaining. And generally, this remains flat for quite a long time, which means even if you prune a big fraction of your feature space, you will still be having like 95% of your variance. Yes, question?
Professor, so U is a matrix of eigenvectors you want to K?
Yes. So U, in this case, we showed it. We showed the intuition using a single eigenvector, but effectively we just calculated the largest showed that the largest eigenvector is the one that maximizes the variance if you project it into one dimension. But if you want U to be larger, then or rather if you want K to be larger, this was K equals 1. If you want K to be larger, then just do the full eigen decomposition rather than just this optimization, because this just gives you the top eigenvector. So instead do the full eigen decomposition and hold on to the top K eigenvalue eigenvector pairs. Okay. Any questions in this so far? So for those of you who may be familiar with singular value decomposition, what we performed here is also called singular value decomposition. So SVD, let me write it here. Okay. Maybe we covered this in one of the earlier lectures, but if you have a matrix X where X is square and symmetric, then X has orthogonal eigenbases eigenvectors and real eigenvalues, right? And if X is positive semi-definite, then it is obviously square and symmetric, and if it's also PSD, then eigenvalues are positive. All the eigenvalues are positive, right? Now, in this case, we are using X transpose X to be the matrix on which we are performing eigen decomposition. So it is X transpose X is guaranteed to be square, symmetric, and positive semi-definite. Right? Now, performing eigen decomposition on X transpose X is the same as performing singular value decomposition on X. Right? The way you go about doing singular value decomposition on any matrix X. In this case, to do singular value decomposition, your matrix need not be PSD, it need not be symmetric, it need not even be square. You're given any matrix whatsoever. The way you perform singular value decomposition on any matrix X is to take X transpose X, take the eigenvectors of X transpose X, and the eigenvectors of X transpose X and the eigenvalues of x transpose x will, or the square root of the eigenvalues will give you the singular values of x. Right? So this is the same as performing singular value decomposition on the X matrix, which is, another way to think of the same thing is to construct X transpose X and just do eigen decomposition on X transpose X. Any questions on PCA? In homework, you will see. So here we saw the variance maximizing argument, where if we want to find a hyperplane where if you take the projections, then the variance of the projections, so this distance, this distance, this distance, this is basically the spread of the projected points is maximized. In homework, you will show that this method is equivalent to, or you will see another motivation where if you rephrase the problem as finding a subspace where the projected points are as close as possible or as near as possible to the original points, that is to minimizing this distance. Right? So maximizing the projected variance and minimizing the residuals are equivalent. And in your homework, you will show that if you phrase it as a problem of minimizing the residuals or minimizing or improving the approximation of the projected points to the original points, you will recover the same solution as maximizing the variance. Like there are two different ways to think of PCA. Find a subspace such that the projections are as close as possible to the original points. That's interpretation 2 that you will do in the homework. The interpretation 1 that we saw in the lecture is find a subspace such that the projected points have maximum variance. Any questions on PCA? Okay, great. So let's move on to ICA. So it looks like we're making good progress. So we might be able to finish ICA today. So in ICA, it's a somewhat different problem from the problems we've seen so far. And perhaps to understand kind of the difference of ICA, it might be useful to kind of place together the algorithms we've seen so far. So far we have seen, let's see, I can erase this one. So far in unsupervised learning, we've seen 4 algorithms, right? So the first one we saw was k-means. We started off with k-means, right? And then after k-means, we studied Gaussian mixture models, right? And after Gaussian mixture models, we studied factor analysis. Right? And today, just now we studied PCA. Right? So we've studied 4 algorithms so far, and you can kind of classify them in 2 different ways. Right? So these you can call clustering algorithms, and these you can call them, subspace algorithms. These were probabilistic, and these were non-probabilistic. Right? So the probabilistic algorithms, we solved them using EM, expectation maximization. Whereas the non-probabilistic problems, in the non-probabilistic approach, we didn't have to use EM. right? And loosely speaking, again, this is a very loose analogy. You can think of clustering problems to be the counterpart of classification problems from supervised learning. Right? You can think of them as classification problems where you're not given the labels, and you can think of these subspace finding problems as the counterpart of regression problems from supervised learning. Okay? And there, both PCA and factor analysis. In both of these, we recovered a low-dimensional subspace, where in factor analysis, Z's were the subspace, Z was the subspace. And in PCA, the way we recover the subspace is to construct the matrix U, where U is the there are k different columns, each of dimension d, and these are the top k eigenvectors of x transpose x, right? And then using this U matrix, which is we can multiply U x transpose. So U x transpose will give us U x transpose will give us k such, or it would be easier to just do it as U transpose. So x U transpose will give us the projected points of x onto the lower dimensional space. Right? You take the eigenbasis and take each example and multiply it and just multiply it onto U. So that's like projecting it onto U because they have unit lengths, and xu will give us the subspace. Now, you might ask what else is different between factor analysis and PCA. The other difference in factor analysis, we assume D was much bigger than N, but here we made no such assumption. Here in fact we assume that N will be bigger than D. If we don't assume N is bigger than D, then again this would it might work. If this would be singular, but yes. So in fact, actually, in PCA you probably don't need to make N to be bigger than D, but it's commonly the case that N is indeed bigger than D. And the other difference between the two was in factor analysis we recovered the matrix L, right? And L, the parameter that we recovered, took us from Z to X. Whereas in PCA we recover U. U takes us from X to Z, if you call Z as the projected points. Right? So the recovered parameters kind of go in opposite direction between factor analysis and PCA. The other difference between PCA and factor analysis was in PCA, you can first perform PCA, get the set of all eigenvectors and eigenvalues, and then decide after the fact what is the appropriate k for your problem. You can decide k after you perform PCA. Whereas in EM, you need to decide k first and then run EM. If you're not satisfied with it, you need to change k to a different value and rerun factor analysis all the way again. Right? Whereas in PCA, you first perform eigen decomposition, and then you look at what k will give you the best variance retaining factor. This question?
Is this a feasible idea to do PCA first to find k and then go to factor analysis?
So the question is it reasonable to first do PCA to find k and then go to factor analysis? But then what's the point of going to factor analysis, because you would have recovered a lower dimensional subspace anyways? right? So these are some ways in which we can classify what we have covered so far. And now we are going to start ICA, independent component analysis, right? And independent component analysis is somewhat different in nature from what we've seen so far. Yes, question?
Is there any advantage of doing factor analysis if it's difficult to implement, if it does not tell you K prior?
So is there a benefit of doing factor analysis? It so happens that so factor analysis, let's think. There are benefits to doing factor analysis. For example, when D is much larger than so this would also.
In PCA, we made no such assumptions, so it will work.
Yeah, PCA it worked, but the problem with so here's the thing. In PCA, we are not explicitly modeling the noise in the data, right? So there was no probabilistic assumptions being made. Whereas with factor analysis, even though you choose K to be some value, it generally works pretty well because it will end up adjusting your the psi matrix accordingly if K is different. So it's quite you can think of them as two different kind of equivalent approaches. The differences are what we discussed. In some cases it makes sense to use factor analysis, some cases it makes sense to use PCA, but PCA happens to be more commonly used because it's easy to implement. You just perform eigen decomposition and you get it. Whereas factor analysis, it also provided us a good example to apply EM. So when we applied EM, in one case Z's were discrete, but here we saw Z's were continuous, right? So it was as an example to understand EM better, factor analysis is helpful, like from an educational purpose. But PCA is probably used much more commonly in practice than factor analysis. Right? Another thing about PCA that we kind of skipped over was we just said do eigen decomposition on X transpose X. But sometimes X transpose X can be, really huge in terms of, the number of dimensions. And, if you were to use NumPy or MATLAB and, do, eigen decompose on a large matrix, then, that may just fail. You may run out of memory or something. So, in fact, when you run PCA in practice, a common technique to perform eigen decomposition is to use something called power iteration. Right? So power iteration is one of the commonly used techniques to perform eigen decomposition on large matrices. Again, this is not going to be something you're going to be tested on, but the idea of power iteration is to start with some U0 and randomly initialized U0, anything that's non-zero, right? And from U0, calculate X transpose X times U0, right? So U1 will be X transpose X times U0 divided by the norm of X transpose X times U0. So basically, take some randomly initialized matrix, randomly initialized vector, multiply it by the matrix whose eigenvector you're interested to calculate, and you get U1. Then multiply, X transpose X times U1 will give you U2, right? And if you keep multiplying the vector over and over again by the same matrix, and after every multiplication, if you rescale it to have unit length, and if you repeat this over and over, you will end up you will see that you will the vector that you'll end up in, the vector that you converge will be the largest eigenvector. Right? The intuition there is suppose this is x1 and xd. Now, if you remember, if you take a unit sphere in your input space and multiply it by a positive definite matrix, then the outputs will be on some kind of an ellipse, right? So if you were to take this as the input, and if this is u naught, multiply it through x transpose x, then you may get this to be the point that got mapped to. So this would be x transpose x times u naught, and then rescale it back to unit length, multiply it through x, and you will get this, and then rescale it back, multiply it through x, and you will get this, and eventually you will see that this will always converge to the principal axis of the ellipse, which is the eigenvector. Right? So multiplying the same matrix, the matrix over and over, and then rescaling the multiplied vector back to unit length. If you repeat that over and over, no matter where you start, you will either converge along this direction, or if you start here, you will end up converging along this direction. But that's going to be your principal eigenvector, right? And then you can then take x transpose x, subtract from it u transpose, you will get a matrix of one lower rank, and then perform the same power iteration on this matrix, and you will recover the next largest eigenvector, and so on. So in practice, usually you do something like this when the number of dimension is large. So this is called power iteration. This is just a good detail to know if you come across the word power iteration. Basically what's happening is, take a vector and repeatedly keep multiplying it by the same matrix and rescaling the length back to 1. Anyways, ICA. In ICA, the motivation is probably best seen through this cocktail party problem. Right? In the cocktail party problem, assume there are D speakers, people who are speaking, and there are D microphones. Right? So there are D speakers and D microphones, and the D microphones are placed in different places of different lengths, and they are recording the D speakers simultaneously. Right? And we will call S in RD to be, think of S in RD to be one instantaneous recording of the speeches that are happening at the sources, right? And we also assume that the recordings in the D microphones, we will call it X. It's also RD, and we assume that X is equal to A times S, where A is commonly called as the mixing matrix. Right? So S J I is the thing that the ith speaker is pronouncing at the jth time, right? And similarly, X I J is the recording in the jth microphone at ith time. Did I say it the other way? So J is the speaker identity. Maybe I told it the other way first time. And I is the time. And similarly, J here is the microphone identity, and I is the time. right? So what's happening is we have D different speakers saying whatever they are saying. And D different microphones that's recording them. So we have speaker 1 over here, speaker 2 over here, right? Let's just start with 2, right? And we have microphone 1 over here, right? And microphone 2 over here. That's recording what they're saying. So this is X1, X2, S1, S2. Now these are kind of placed at arbitrary distances from the speakers. We will assume there is no lag in recording, and let's say speaker 1. Let's assume this is the waveform of what the speaker 1 is speaking, right? And speaker 2. Right, this is the waveform of what speaker 2 is speaking, right? And this is time, right? Time is progressing this way. And if we take a point in time and record a snapshot, right, this will give us Si. So at time I, Si will be set Si1, Si2, right? And this is in our D. Here D equals 2, right? So the Si1 is this height, Si2 is this height, right? And this is the time. So you can think of a snapshot in time to be one example, and the kind of the amplitude of what the speaker is speaking at that time to be the coordinate value at that example, right? And similarly, we have the two microphones, right? So this is microphone 1, X1, X2, and this microphone is recording some linear combination of the two. This is X1 and this is X2, right? Similarly, over here, again, time is moving to the right, and at time I, Xi is equal to Xi1, Xi2, where here these are the values recorded by the microphone at time I. We will assume that we have the same number of microphones as the number of speakers, and we are only observing these x's. And the problem now is we are only given these x's. We are told the number of, we obviously know the number of microphones. We assume that there are the same number of speakers. And by only having these D different microphone recordings, we want to recover the original speech signal spoken by each speaker. Right? That's the setting in which we want to in which we are operating. And and what that translates to essentially is we make the assumption that x equals as, which means xi equals a of si. Right? A is a square matrix because we have the same number of speakers as the number of microphones. And what we want to do is to calculate W is equal to A inverse which is called the unmixing matrix. Right? W equals A inverse is the unmixing matrix where W can take X, right, and return S. Right? So the W matrix can separate the speaker. So this is also called the source separation problem, where we are given X's which are different mixtures of the sources, and using just these mixed sources we want to construct this W matrix. It's called the unmixing matrix, which will recover back the original speech. Right? And the assumption that we are going to make only one assumption. The one assumption that we are going to make is that SIs are distributed, are independent in the sense each SJ is independent of the other SJs. So the assumptions we are going to make are so what are the assumptions we've made so far? So the first assumption we made was number of speakers equals number of microphones, right? And the second assumption we made was that these two are associated with a linear relation. So S is equal to WX, right? We made a linearity assumption. And the third assumption that we're going to make, which with just these two, it's impossible to recover. Right? We need to make some more assumptions. The assumption that's going to help us recover is that we're going to assume Sj is independent of Sk, where j is not equal to k. What that means is Sj has some kind of a probability distribution, and Sk has it belongs to another probability distribution, and these two random variables are independent. Right? What that essentially means is we are assuming that what one speaker is saying is independent of what the other speaker is saying, which may not be a valid assumption in reality. If two people are having a conversation, then most likely only one of them is speaking at a time, etc. But it generally turns out that this still happens to be a reasonable assumption to make. Right? So independence assumption, and we need to make one more assumption that will allow us to solve this problem. The last assumption that we are going to make is that Sj is not Gaussian. Right? So this is a non-Gaussian assumption. Right? Why do we need to make this non-Gaussian assumption? Let's see a few pictures, and hopefully that will give some intuition. Right. So these are basically the slides we saw in the intro lecture. Just well, let's hope the audio works. So here we have we're considering the case of d equals 2, and these are the versions that are recorded in the microphones, the two microphones, and these are what the original speaker said. Right. So
1, 2, 3, 4, 5, 6,
It's basically two speakers counting 1 to 10, one in English and the other in Spanish. And this is a recording from another microphone. The audio is a little low, and once it's separated, it sounds like this. Can people at the back hear it? Okay.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Right, and the other one, once it's separated.
1, 2, 3, 4, 5, 6, 7, 8, 9, y 10.
Right? So all that was fed to this algorithm was these two mixed clips and nothing else. And by making certain independence assumptions and linearity assumptions, the algorithm was able to recover these separated versions of the two audio clips. Right? And to understand these assumptions, I made a few slides that might, yeah. So let me open it in preview. Right? So what do we have here? So we assume that Si and Sj must be independent, and we also assume that each of the Sj's must not be Gaussian. So the first row, all the three rows correspond to Gaussian distribution. The second row, all the three correspond to Laplace distribution, and a third, all the three correspond to logistic distribution. So if in the case of Gaussians, here x1, the x-axis and the y-axis represent two independent Gaussians, and each point in this cluster of points are points that are sampled from a joint Gaussian distribution where the two components are independent. So if we sample from two independent Gaussian distributions, assume both have mean 0, variance 1, then you will see that the points are generally the clustered points have this circular formation, right? And then we apply some kind of a linear transform. So the first column corresponds to one linear transform. The second column corresponds to another linear transform. The linear transform is applied to the points that were sampled here, right? And we see that if so the first column corresponds to a linear transform that was more or less just a rotation. We see that the rotated version looks exactly like the original version if it's Gaussian, right? If it is some other some other kind of a linear transform, then it gets some kind of an ellipse shape, right? Now, instead of Gaussians, let's assume we start with two independent Laplace distributions, right? Where the source 1 and source 2 are sampled according to independent Laplace distributions. We see that the shape taken by the product of two independent Laplace has this kind of it has this diamond shape, right? And then if we apply linear transformations, we get shapes that look like this. And similarly, if you start with two independent logistic distributions, when they're independent, they look like this. And as you apply transformations, they take different shapes. In ICA, we are starting with data that look like this, right? The microphone recordings, if you were to plot them, they look something like this. And given these, when we start, if we were to start with data that looks like this, and we want to recover the original untransformed data, with Laplace and logistic, we see that we can make a good guess. The corners correspond to corners, etc. But in case of Gaussian, it's hard to tell whether in fact, it's impossible to tell whether this transformed data came from this version as the source or this version as the source, right? Because in Gaussians, you have these smooth ellipses, and there is this rotational ambiguity of not being able to determine what the original shape was. Whereas with these other distributions, they do not have this smooth ellipse shape. They have these, the intuition to have is that you have these corners, right? And these corners can correspond to one of these corners. These non-Gaussian distributions still do have the ambiguity that the axes can be permuted, right? You can construct unmixing matrices that start from here and map you back to the unmixed versions where the axes are permuted, because one corner can get mapped to a different corner, right? And you can also have ambiguity that the axes are flipped in their sign. However, though in problems where those ambiguities are tolerable, ICA works very well. Which means, for example, if you're applying ICA to audio source separation, once we unmix the mixed audio clips, we recover the original audio clips, but the speaker 1 and speaker 2 identities may have shifted. But that's okay because we never knew what the original identities were. Right? In case of ICA, once we run ICA and recover the unmixed versions, there is no guarantee that the first column of or the identity of the first source will always be the same. Right? There is ambiguity about what the original sources are, and there's also ambiguity that the sign is flipped. And in audio, generally, that's okay too. The sign of your wave file can flip, and you'll still get the same audio. Right? So this gives us some intuition of the ambiguity that arises only in Gaussians. Right? This spherical shape is characteristic of the Gaussian distribution. Right? In no other distribution, if you multiply the PDFs of two independent distribution, no other will give you a contour map that is spherical. The spherical shape comes only from the Gaussian. So as long as the distribution of our sources is assumed to be non-Gaussian, we have some hope of recovering the original signal. Yes, there was a question?
In theory, we do need to care about this last assumption, but in practice, no one actually speaks according to a distribution. So does it ever matter what the last assumption happens?
Yeah, so the question is, in practice, nobody actually speaks according to a Gaussian or a Laplace, right? What's the does it actually matter? It actually does matter a lot. In fact, that's the only thing that matters, because even though your data may not be distributed according to a Gaussian, what I'm about to show in the next slide here is that these two clusters that we see are in fact. So I just took the waveforms from the two audio clips that I played a few minutes ago and just plotted a scatter plot of the corresponding audio amplitudes from the two sound clips. We see that in the separated version, even though they are not Gaussian, it is still not spherical, right? So there is some amount of you can kind of see that there is some elongation along this axis and there's some elongation on this axis, and it's not perfectly spherical. So when we start with the mixed version, so this is basically the scatter plot of the mixed audio clips, right? We see that the algorithm is able to recover the two independent components, even though the data was not actually distributed exactly according to a Laplace or logistic, right? So that's some intuition to show why non-Gaussian assumption is important. So with these two assumptions, so with these two assumptions, we can now formulate ICA. And we we need one final thing to take care of, which is the linearity assumption. So, supposing we have a random variable, let's assume it is uniformly distributed between 0 and 1. It's a uniform random distribution that lies between 0 and 1. Right? So, x is uniform. Let me take a different pen. Uniform between 0 and 1. This pen's better. Right? And so which means x looks like this, 0 and 1, and the PD of x looks like this. So this is x, this is P of x. So it has density equal to 1 between 0 and 1 and 0 everywhere else. Right? So this is just a uniform random variable over 0 and 1. Now what about 2x? Right? What is, let's consider y equals 2x. What is P of y? So what's P of, so when we do y equals 2x, now y will be distributed between 0 and 2. Right? It has density 0 outside this region. What is P of y between 0 and 2? Half, right? This is half. Why is this half? Right? So exactly. So the probability distributions require that the area under the PDF must integrate to 1. Right? So if we stretch the x-axis, we have to shrink the y-axis by a corresponding amount, and that's because the area under the PDF must integrate to 1. Right? Now, what happens in a higher dimension? If x is, in general, x instead of one axis, let's assume this is some script x, right? And instead of multiplying it by one scalar, we do y equals, say, some y equals w x, where w is some matrix. Now x is in Rd. This is Rd by d, and y is again in Rd, right? And we have p of x to be some x, to be some value. So p of y will be, what can we say about p of y? P of y will be, p of y is wx, right? So let's assume this is the density of y and this is the density of x. Is this correct? This is not correct, right? And it's not correct because of the same reason, where p of y had to be, so py of y had to be px of 2x times 1 over 2, right? So similarly, here we need to divide it by the determinant of w, right? This determinant of w, you might have seen this from your probability theory course. This is also called the Jacobian. So Jacobian, whenever you perform a change of variable of your random variable, the density will be transformed according to this extra Jacobian. Right? Yes, question?
Is it p of y, py is y, it is px of x times half or px of 2x times half?
Sorry, this should be py. Yeah, because py is sorry. So py of y is px of x is y by 2. Yeah, y by 2 times p times half. Does that make sense? And what did I write here? I think here also so this, if similarly if P of y will be W inverse of y, W inverse of y times 1 over W, right? Right. So whenever we transform a variable, some linear transform, the density will get this extra determinant factor. Right? With these pieces, in fact, we are ready to finish ICA. Right? So in ICA, we define P of x to be product from j equals 1 to d Ps of W j transpose x times W. Over here, W is the unmixing matrix where Wj times some x will get us back the jth source. Right? So Wj is the unmixing matrix. You give it this mixed x, you multiply it. Each Wj times x will give us Sj. Right? So this is Sj. So Sj equals Wsj times x. So Wj times x, and we define the probability of x as in terms of P of s, and we make the assumption that P of s is distributed according to the logistic distribution. So the logistic distribution is the distribution whose CDF is the logistic function, right? So if you remember, the logistic function is P. So the CDF or CDF of x is equal to 1 over 1 plus e to the minus x. So this is the CDF of logistic. You can call this sigma of x, and so the PDF, the probability density of the logistic, f of x, is the derivative of this. That's basically sigma of x times 1 minus sigma of x, where sigma is the sigmoid or the logistic function, right? And using this, so this sigmoid x times 1 minus sigmoid x will be Ps of x. So we assume that the sources are distributed according to the sigmoid distribution, which gives us, we can write the L of W, where the parameter here that we are training is W, is sum over I equals 1 to n, sum over j equals 1 to d, log of the PDF, which is sigmoid of x times 1 minus sigmoid, so xi times 1 minus sigmoid of xi, right, plus log determinant of W. Right? So the parameter that we are interested here is just W. Previously, the parameters that we were trying to recover happened to be the parameters of the of the probability distribution itself. For example, we would define the likelihood over mu or sigma or some such thing like that. Here, the parameter that we are trying to learn is this the transformation W that's going to take us back into something that is distributed according to sigmoid. And using the linear transformation, we get this extra log determinant term, due to the extra determinant that came due to the Jacobian, right? And that's all there is to it. You take this objective, take the derivative, perform gradient descent, and run gradient descent until you converge, right? And the corresponding update step, so you take the derivative of this and you get the update step that looks like this. W equals W plus alpha, some learning rate, times 1 minus 2 G, here G is just the sigmoid, 1 minus 2 sigmoid of W1 transpose Xi, 1 minus 2 sigmoid W2 transpose Xi, and so on, times Xi transpose plus W transpose inverse, right? So this is the update rule, right? And you can perform stochastic gradient descent, and once this converges, take the converged W, multiply your x's with W, and you get s's. And if you play these s's, you write it into a wave file and you play these s's, they will be separated, right? It's almost magical, it works. And in your homework, so here you have the update rules for assuming that PSs were logistic, and in your homework you will do it. You make a small. You try it with a different distribution. You assume it's Laplace distributed, and in your homework you have 5 different audio clips instead of 2 audio clips, and run it till it converges. Take the resulting unmixing matrix, the converged unmixing matrix, and multiply your mixed audio clips through it, and you will recover a new audio clip. And you play it, and they should sound well separated. And one final tip for your homework: in the logistic distribution, you will encounter the absolute value of x, and you'll have to differentiate it, right? And the what's d by dx of the absolute value of x?
It's a split, right?
Yeah, it is split. So absolute value of x looks like this, right? So it has slope -1 when it's negative and slope +1 when it's positive. So d by dx of the absolute value of x is just the sine of x, right? So you'll need that for your homework. You would have probably figured it out, but in case you are struggling, the derivative of the absolute value of x, this is the sine of x, and with this you can replace the sigmoid PDF with the Laplace PDF, take the derivatives, derive a different update rule, and run it on the audio clips, and you'll be able to recover them. And so that basically covers PCA and ICA. Any other questions? If you have questions, walk up to the stage here. Happy to take questions.